Hey there, it's Shannon Math Chick Myers, and today we're looking at section 7.2.2 from the ZIL Intro to Differential Equations text. And we're covering the Laplace transforms of derivatives so we can actually solve a differential equation that's linear in form with constant coefficients using the Laplace transform. Okay, our evil plan for this section is to use the Laplace transform to solve differential equations, specifically initial value problems. Therefore, we need to evaluate quantities such as L at dy dt, that's the Laplace transform at that first derivative of y with respect to t, and L at that second derivative of y with respect to t. If f prime is continuous for t greater than or equal to 0, then L at f prime at t is going to equal to, so this is just that general definition for a Laplace transform, the integral from 0 to infinity of e to the negative st times f prime at t with respect to t. And that, of course, will be the limit as b approaches infinity of the integral from 0 to b of e to the negative st times f prime at t, all with respect to t. So we have to use integration by parts on this. So when we do our integration by parts, let's see what we get. We'll have u is equal to e to the negative st. So du will equal to negative s times e to the negative st. dv then will be f prime at t dt. So v will just be f at t. So putting it together, we'll have the integral of u, which is e to the negative st, dv, which is f prime at t dt, is equal to u times v. So we'll have e to the negative st times f at t minus the integral of v du. So let's see, minus a minus is plus, so and we can factor out the s because it's not part of our integral. And then, or our, limits of integration on the integral. And then this is going to go, let's see, we will have e to the negative st times f at t dt. Groovy? All right. So now bringing that back over, all right? So this is done. I know it doesn't look very done, but it is. We will have, all right, so we'll get L at f prime at t equals, we'll be taking the limit as b approaches infinity of the first part of our result, which was e to the negative st times f at t, and we'll be evaluating this from 0 to b, plus s times the integral from 0 to infinity of e to the negative st times f at t dt. Sorry about the dogs. They howl. Got two out of three of them. All right, so this one's going to be equal to the limit as b approaches infinity of to the negative sb times f at b minus e to the negative s times 0 f at 0. And then this next part here is s times the Laplace transform of f at t by definition, right? So let's see what we get. Now remember that f at b doesn't grow faster than e to the negative sb by definition, like as part of the requirements for a Laplace transform. So this here is going to go to 0. So we'll get 0 minus f at 0 plus s times that Laplace transform of f at t. And that's just going to be s times that linear transform or Laplace transform of f at t minus f at 0. Groovy? So this is, one you want to remember. Now it turns out that similarly, right, you'll get, if you are looking at the Laplace transform of f double prime at t, that's going to be s squared times, I'll just keep it in terms of the Laplace transform, L at f at t minus s times f at 0 minus f prime at 0 and L at f triple prime at t ends up being s cubed times L at f at t minus s squared times f at 0 minus s times f prime at 0 minus f double prime at 0. So if you see that trend, it turns out that if f prime, f double prime, all the way to the n minus first derivative of f are continuous on 0 inclusive to infinity non-inclusive, and they are of exponential order, and if the nth derivative at t is piecewise continuous on 0 to infinity, then the Laplace transform of the nth derivative at t is going to be s to the n times capital F at s minus s to the n minus 1 times lowercase f at 0 minus s to the n minus 2 f prime at 0 minus minus f to the n minus first derivative at 0, where capital F at s is equivalent to the Laplace transform for f at t. All right, so solving linear ordinary differential equations. So since the Laplace transform of that nth derivative of y with respect to t depends on capital Y at s, which is equal to L at y at t, and the n minus 1 derivatives of y at t evaluated at t equal to 0, the Laplace transform is well suited for solving linear initial value problems where the dE has constant coefficients. So this whole big equation, a sub n times the nth derivative of y with respect to t, plus a sub n minus 1 times the n minus first derivative of y with respect to t, all the way down to a sub 0 times y equal to g at t, where we're given these initial conditions. Y at 0 is y0. Y prime, sorry, that's a typo, at 0 is y1. Dot, 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 y to the n minus first derivative at 0 is equal to y sub n minus 1, where the ai, I equal to 0, 1, 2, dot, dot, dot to n, and y0, y1, dot, 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 all the way to y sub n minus 1 are constants. By the linearity property, the Laplace transform of this linear combination is the linear combination of the Laplace transforms. And so we will have a sub n times s to the n, the Laplace transform at f at t, or y at t, is capital Y at s, and then minus s raised to the n minus 1 times y at 0, minus s raised to the n minus 2 times y prime at 0, minus dot, 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 minus y raised to the, or y to the n minus first derivative at 0. Then you've got the next one, right? So you'd keep going, and you would end up having, plus a sub n minus 1 times s to the n minus 1, capital Y at s, minus s to the n minus 2, y times lowercase y at 0, minus dot, 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 minus y, the n minus second derivative of y at 0. And then you'd keep going on like that, plus dot, 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 plus, until you got to a0 times capital Y at s is equal to capital G at s, where L at y at t equals capital Y at s, and L at g at t is equal to capital G at s. So to isolate y at s, we let p at s times y at s equal to q at s plus g at s. Those are capital. So what you'll end up with is y at s is going to equal to q at s over p at s plus g at s over p at s, where p at s is equal to some polynomial a sub n times s to the n, that is in s, plus a sub n minus 1, s to the n minus 1, plus dot, 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 plus a0, and q at s is a polynomial in s of degree less than or equal to n minus 1. So steps. You apply the Laplace transform, L. You solve the transformed equation for y at s, capital Y at s, and then you apply the inverse Laplace transformation, L inverse, to solve for your y at t. Okay? So, all right, let's do this thing. Just to finish this off, this would be y at t. Cool? All right, so use the Laplace transform to solve the given initial value problem. So we have 2 dy dt plus y equals 0. And so applying that Laplace transform to both sides, we'll get 2 times L at dy dt plus L at y is equal to 0. And then we will have 2 times s. So now we're looking at this formula, right? We have the first derivative, so we'll have s to the 1, all right, times L at y minus y at 0. So L at dy dt is this stuff here, following the theorem, plus L at y equals 0. So that gives us 2 times s times L at y minus 2 times y at 0 plus L at y is equal to 0. I'm going to factor out an L at y on the right, and then I'll be left with 2 times s plus 1, and then minus 2, y at 0 is negative 3 from the given initial conditions, and that's going to all equal to 0. That should be equals negative 3. And then we will have L at y equals, so 2 times negative 2 times negative 3, that's plus 6. And so I'm going to get a negative 6 when I bring it over, and then I have to divide by 2 times s plus 1. Now I have to get this in the form where it will look like an inverse, or where I can get the inverse, right? So L at y is equal to, I can go ahead and divide each term by 2. So that's going to give me that L at y is equal to negative 3. I'm going to factor that out, times 1 over s minus negative 1. And that's the format using the theorems from that last section, where we'll get e to the negative t, negative 1 times t. So applying the inverse transform, right, to this stuff, we will have y at t equals negative 3 times L inverse at 1 over s minus negative 1. And finally, y at t equals negative 3 e to the negative 1 times t. And we're done. Isn't that groovy? Now this next one, I don't know how groovy you're going to find this one. There's a lot of algebra. In fact, so much so that I decided midway through that it would be ridiculous for you to do the partial fraction decomposition by hand. So I'm going to introduce you to a free one online. But here we go. So we have y double prime minus 4y prime is equal to 6e to the 3t minus 3e to the negative t. And we've been given these initial conditions. So we apply our Laplace transform to each side. And then, working through it, we will have L at y double prime minus 4 times L at y prime is equal to 6 times L at e to the 3t minus 3 times L at e to the negative t. So, plugging in for L at y double prime, we're going to have n is 2 in this case because it's the second derivative. So we're going to have s squared times L at y minus s times y at 0. This is all from that theorem we had in this section. And then minus y prime at 0. So this one here is all of this. Cool, cool? Minus 4 times L at y prime. So that's just going to be s to the 1, because it's the first derivative of y, times L at y minus y at 0. All right, and then that's going to give us 6 times, we just did this, right? L at e to the 3t, isn't that just 1 over s minus 3? And then minus 3 times L to the e at the negative t is going to be s minus negative 1, so s plus 1. All right, so let's do this thing. We have 2 of the terms have L at y in them, right? So s squared minus 4 times s takes into account both of those L at y's. And then I'll have minus s times y at 0 minus y prime at 0, and then plus 4 times y at 0 is going to be 6 over s minus 3 minus 3 over s plus 1. Cool, cool? All right, so continuing, s squared minus 4 times s times L at y. Y at 0 is 1, so we'll have minus s times 1. Y prime at 0 is negative 1, so minus a negative 1 plus 4 times 1 is equal to. So I'm going to get a common denominator with these two guys, and we'll have 6 times s plus 1 minus 3 times s minus 3 all over s minus 3 times s plus 1. Continuing work on the left-hand side, we'll have s squared minus 4s times L at y. And then this is going to be minus s plus 5 is equal to 6s plus 6 minus 3s plus 9 over s minus 3 times s plus 1. Now, we want to isolate L at y. So, let's see what this looks like. Simplified, we have 3 s's, right, plus 15 over s minus 3 times s plus 1, and then s squared minus 4s, because we'll be dividing by that. And then we will have plus s minus 5 over s squared minus 4s. Cool so far? Now, I need a common denominator, right? So I'm going to go ahead and continue this out and multiply by s minus 3 times s plus 1, just that second fraction. And then same with the denominator, so we're multiplying by 1. So we will have L at y is equal to 3s plus 15 plus s minus 5, I'll get the second 2, times s squared minus 2s minus 3 all over s minus 3 times s plus 1 times s squared minus 4s. L at y will be equal to 3s plus 15 plus s cubed minus 2s squared minus 3s minus 5s squared plus 10s plus 15 all over s minus 3, s plus 1, s squared minus 4s. Almost there. So L at y is going to be, combining like terms, the 3 s's zero out. We'll have s cubed minus 7s squared plus 10s plus 30 all over s minus 3, s plus 1. Now, if you were doing this by hand, you'd want to write it as s times s minus 4. But I'm going to take you to this groovy little deal, which does it for us, because I think we did enough work. So here we go. I just Googled, I got to turn off airplane mode, I guess. I just Googled Laplace transforms. So here we go. We had, for our numerator, not not sure if it'll let us do things in terms of s. We'll find out. We have s cubed minus 7s squared and then plus 10s plus 30. Whoops. And then over we have an s minus 4 I'm going to start over. We have an s. We have an s minus 4. We have an s plus 1. We have an s minus 3. Not p. All right, let me see. S minus 4, s plus 1, s minus 3, and an s. Perfect. And then I'm going to say equals perfect. It did it in terms of s. And look at this. Here's our partial fraction decomposition right over here. Groovy? So and then we've got our partial fraction expansion. So I'll just copy that over. So that gives us negative 2. Actually, I'll write it in a friendly form to get the inverse. We'll have negative 2 times 1 over s minus 3 plus 5 halves times 1 over s minus 3/5 times 1 over s minus negative 1 plus 11/10 times 1 over s minus 4. And then when we apply the inverse Laplace transform, and the linearity, we're going to end up with y at t is equal to negative 2, the Laplace transform, inverse transform for 1 over s minus 3 is e to the 3t plus 5 halves times 1, right? Minus 3/5 times e to the negative 1 times t plus 11/10 times e to the 4t. And these are the inverse transforms. So at the end of the day, y at t equals 5 halves minus 2e to the 3t minus 3/5 e to the negative t and plus 11/10 e to the 4t. And we're all done. So if you want to do that partial fraction decomp, this was Wolfram alpha. You can do it by hand. This is like kind of a handy dandy little app there. Cool, cool? All right, I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. If you like what I'm doing, hit that subscribe button and like the video. Thank you. Bye.